Next topic is crystal field splitting in tetrahedral complexes. Hanji students, last time we have discussed crystal field splitting in octahedral complexes. Now second topic is crystal field splitting in tetrahedral complexes. Coordination number for tetrahedral complexes is 4. So there will be central metal ion at the center of the complex and 4 ligands around the central metal ion. How we will represent tetrahedral complex, the tetrahedral arrangement? Then this is represented by a cube in which central metal ion is at the center of the cube and 4 ligands are present at the 4 corners, and that will be at the 4 corners, that will be alternate positions. And in this, as we take this ligand, this is the ligand, this is the ligand, and this is the ligand. So first ligand is there, then one alternate position, then this is the ligand, alternate position, then this is the ligand. So there are ligands present at alternate positions. These ligands can be written at these positions: 1 ligand, 2 ligand, 3 ligand, and 4th ligand in this direction. At these positions also there will be arrangement of 4 ligands around the central metal ion. So we will represent 3 axes. One is the x-axis, y-axis, and z-axis, and the orbitals that will be in between the axis dxy, yz, and dzx point between xy and z-axis, that is towards the center of edge of the cube, whereas orbitals dx square minus y square and dz square that point along the xy z-axis, so that is the centers of the faces. So now we will learn, in tetrahedral field, none of the d orbitals that point exactly towards the approach of the ligands. Means if we take dxy, dyz, and dzx orbitals, that will be in between the axes. So in between the axis means these will be this axis, for example. So these axes will be near to the approach of the ligands, whereas 2 axes, that is along the principal axis, that there are no ligands that exactly towards the dx square minus y square and dz square. So 3 orbitals dx square, dxy, dyz, and dzx, that is in between the principal ligands, and also ligands are present in between the principal axis, so they just close to each other, so there will be repulsion and there will be increase in energy of 3 orbitals dxy, dyz, and dzx. But none of these ligands that exactly point towards the approach of none of the ligands that it will be exactly towards these axes, these orbitals dxy, dyz, and dzx, whereas dx square minus y square and dz square, that is in between the ligands, so none of the ligands are present along the dx square minus y square and dz square, so there will be less repulsion, there will be decrease in energy. So there will be splitting of d orbitals into 2 sets. One will be containing 3 orbitals, other will be containing 2 orbitals. 3 orbitals, that is dxy, dyz, and dzx, these energies are high, as in this these are energy high, and 2 orbitals dx square minus y square, that is having lower energy. So 3 orbital set, that is represented at T2, whereas 2 orbital set, that is represented by E. And in this, why we do not use G term? Last time in octahedral complexes we have used T2G and EG. In this we use only T2 and E orbitals, we don't use G orbitals. So question is there, why we don't use G term in case of tetrahedral complexes. So firstly we will see the free metal ion as diagram. So these are the free metal ion in these 5 degenerate d orbitals. As all the ligands are approaching to the central metal ion at equal distance, so energy will increase all the orbitals at the equal distance, so still they are degenerate orbitals. Next, if we take, then there will be splitting into T2 set and E set, and the gap is called delta T. Gap is called delta T, and delta T is equal to 10 dq. So delta T is equal to 10 dq, and this is E set is stable by 6 dq, whereas T2 set is unstabilized by 4 dq energy, and there is also barycenter rule, that is center of gravity rule. So this is, there will be 10 dq energy level. So delta T is equal to 10 dq. So this is also equal to delta T is equal to 10 dq, that is tetrahedral splitting. So this is the diagram in tetrahedral complex. So next question is कि why we do not use G term in case of tetrahedral complexes. There are two terms, G and U. G is for G-red and U is for un-G-red. So that terms are only for those fields in which having center of symmetry, या ਆਪਾਂ ਕਵਾਂਗੇ these are applicable only for centrosymmetric molecules, as octahedral complex that is having center of symmetry and that is a centrosymmetric molecule, whereas tetrahedral case that is having no center of symmetry, so that is not a centrosymmetric molecule. That's why we do not use G or U term. We only take E and T2 set. T2 means 3 orbitals dxy, dyz and dzx, whereas E set that means dx square minus y square and dz square orbitals. So this is important question. Next question is, there is delta T value is equal to 4 by 9 delta O. This is the value, and in this there is splitting, crystal field splitting in tetrahedral complex that is less than the octahedral complexes. Question is, reason for the smaller value of smaller crystal field splitting in tetrahedral than in octahedral complexes. So that's why delta T is always less than delta O, and that is equal to 4 by 9 delta O. And reason behind this is, first reason, in tetrahedral complexes there are 4 ligands, whereas in octahedral complexes there are 6 ligands. So the greater number of ligands and greater will be the crystal field splitting. So in octahedral greater number of ligands, 6 ligands, so greater will be crystal field splitting, whereas tetrahedral having only 4 ligands, so there will be less crystal field splitting. Second case, in tetrahedral complexes, a tetrahedral field, none of the orbitals that exactly point towards the ligand's approach of ligand, therefore splitting is less. In case of octahedral, 2 orbitals dx square minus y square and dz square that point exactly towards the approach of ligands. So in tetrahedral field, none of the orbitals are exactly towards the approach of ligand, so splitting is less. So that's why crystal field splitting in tetrahedral is less than the octahedral complexes, and that is relationship is delta T is equal to 4 by 9 delta O. And next question is, why tetrahedral complexes always form high spin complexes? Because as we learn, tetrahedral complexes, in case of tetrahedral complexes, crystal field splitting is less, and it is even less than the pairing energy. Therefore pairing of electrons will not be energetically favorable, and there will be no pairing of electrons. If there is no pairing of electrons, so they always form high spin complexes. So that's why tetrahedral complexes are always high spin complexes. So these are the three important questions. Next is crystal field stabilization energy for tetrahedral complexes. In this, as we know that tetrahedral always form high spin complexes, and system is this. In this, 2 orbitals will be lower side and 3 orbitals will be at upper side. For example, D1 case, first electron that goes into lower energy orbital E set 1, and this energy is minus 6 dq, and above energy is plus 4 dq, opposite as in case of octahedral complexes. CFSC will be equal to minus 6 dq, so 1 electron, so 1 into minus 6 dq equal to minus 6 dq, and for 2 electrons 2 will be filled into the 2 E set, then 2 into minus 6 dq, that is equal to minus 12 dq. For D3, then third electron that goes into T2 set, and there will be no pairing of electrons. नीचे नहीं जाएगा ये electron E set चे, and above position, and then lower 2 electrons having energy minus 6 dq, and above is having plus 4 dq, so that will be having minus 8 dq. Similarly for D4, next electron goes into T2, then D5, then D6, then pairing, D7, again pairing, D8, above T2 set electron goes into above T2 set, then D9, D10. So because tetrahedral complexes form high spin, so there will be no pairing of electrons. So this is the crystal field stabilization energies for tetrahedral complexes. Thank you, students.